Alright, so we're going to finish up now with our final section on the muscular system, starting off looking at the energy that we use for muscle contraction. So as far as energetically demanding activities go, muscle contraction is right up there. As we saw before, all those myosin heads, if they're going to release from their actin proteins, are going to burn up ATP each and every time they do that. So within really a few minutes of physical activity, not even a few minutes, a few seconds of physical activity, your cells are going to burn up most of the ATP that they have on hand. ATP is a relatively short-term energy storage molecule, and if you start putting heavy demands on the body, like strenuous physical activity, you're going to burn up most of the ATP that you had stored up pretty quickly. One thing that can kind of help with this is creatine phosphate, which is a type of substance found in muscle tissues that help to recycle ATP from ADP. So creatine phosphate, obviously there's phosphate involved, and ATP is in triphosphate. So by throwing all of a sudden a bunch of extra phosphates into the mix, that's going to help turn over ADP and phosphate back to ATP again. So it's going to help synthesize ATP more quickly to help fuel those muscles once you start placing demands on them. But again, the amount of effect that this might create is only a few seconds worth. So, within even a minute, really, of strenuous physical activity, you've really used up most of your ability to produce some ATP, at least in the really short term. As far as where we get the ATP from, we've seen this before. We've seen the use of glucose, we've seen the use of proteins, and we've seen the use of fatty acids to make ATP. All of these methods require oxygen, right? They're all involved with aerobic cellular respiration, so they're going to require oxygen if they're going to work. If oxygen is not available to the extent that you need it, then you're going to switch over to a slightly different pathway. Part of it's going to be the same. The glycolysis part of it is also involved with aerobic cellular respiration. It's the precursor to aerobic cellular respiration. But if you don't have enough oxygen around, if you're burning up more oxygen than what you can bring in and supply to your cells, then you're going to go more into a fermentation pathway. In the case of humans and other animals, that's going to involve the production of lactic acid. This is what typically leads to muscle fatigue. It was thought historically this was also kind of the material that would lead to muscle soreness following a bout of strenuous physical activity. That's less the case than we really thought it was even a few years ago, but it does certainly lead to muscle tiredness in the short term. Once we have lactic acid built up, then it's up to the liver to help convert lactic acid back into glucose. But again, that's going to take some time. That's not a right now sort of a thing. It takes a fairly substantial amount of time for that glucose to be produced from the lactic acid that you've built up. In terms of twitch muscle, fast twitch versus slow twitch, the idea with this is that different kinds of muscle, if they're electrically stimulated, if you give them a little bit of a shock, are going to contract and relax. And the effect of this is sort of like what a neuron would do. It would cause a contraction and then relaxation. But the time that it takes for the contraction and relaxation to occur is what distinguishes a fast twitch from a slow twitch muscle. If you were to take multiple electric shocks to a muscle or stimulations to a muscle in very, very short time spans, those twitches are actually going to build on each other. And if you make it even more extreme, if you make those electrical impulses really, really close together, the muscle is going to go into a state of what's called tetanus, which is where it more or less locks up. It's in permanent contraction without any relaxation at all in between. So based on that, we have two broad kind of ends of a continuum here. We look at slow twitch versus fast twitch. Slow twitch fibers are what's also called a type 1 fiber, and fast twitch is what's called a type 2 fiber. So again, here's the idea of those electrical stimulations over the course of time. If you give them just one quick shock, you get a muscle contraction that looks like this, so it's relatively slight. And then if you give it enough time, if it recovers, it can then do another one of the same amplitude. If you take two shocks in close proximity, so if you shock and then shock again pretty much right after the first one, you're going to get what's called summation, where the muscle is going to contract twice as hard because the peak hasn't quite recovered yet, and the muscle hasn't recovered yet from the initial contraction. It's going to build on itself, in other words. And then over here, if you take several shocks all in a row, they're going to build on each other, and eventually, if it's close enough, they're going to go into tetanus, which is where they lock up completely. Okay, so slow twitch muscle fibers, the type 1 fibers are also what you would typically call, in any other animal except for a human, hopefully, you would call it dark meat. So you think about chicken, turkey, those kinds of things. Dark meat or red fibers or type 1 or slow twitch fibers, whatever you want to call them, are muscle cells that are they're built for endurance. They're built for long-term, not really bursts of power, but long-term exertions of power. They don't contract very fast. They don't recover very fast. They have a lot of strength, a lot of sustained contraction, but not a very explosive contraction. They're going to have a lot of capillaries, so blood supply is going to be high, which is why they are red fibers. They're going to have, on a cell-by-cell basis, a lot of mitochondria to help provide ATP for long-term exertion. And they're also going to have a lot of myoglobin. Myoglobin is a protein that is somewhat similar to hemoglobin in that it binds to oxygen, but it's more, it has a higher affinity for oxygen. So it bonds to oxygen even more tightly than hemoglobin does. So if there's any myoglobin around in that tissue, it's going to help scavenge whatever oxygen might be around, even under relatively low oxygen conditions. On the other hand, type 2 fibers, or what we call white fibers, these have fewer capillaries, they have fewer mitochondria, they have less myoglobin. And all of those things combined mean that these muscles are going to be not so much for endurance, they're going to tire out relatively quickly, but they are very, very good at short, powerful exertion. So rapid contractions, short bursts of power, not endurance, they get tired quickly, they go anaerobic relatively quickly as well, but they do have that short-term capacity for rapid power generation. These tend to be more inclined to go into anaerobic respiration, whereas the slow twitch fibers tend to stay more in the realm of aerobic respiration. Okay, so I mentioned a second ago that this idea of slow twitch versus fast twitch is kind of like having two ends of a continuum, and that very much is the case. If you look at certain muscles are very much on the fast twitch end of the spectrum. The eye muscles, the ones that actually move the eyes around in their sockets, those are fast twitch. There's no doubt about it. If you look at the soleus, which is one of the deep muscles of the leg, the yellow line here, this represents a slow twitch. So the contraction is relatively strong, but it maintains itself over a very, very long period of time, relatively. I mean, we are talking about milliseconds, but compared to like what happens with the eye muscle, this contraction is spaced out over a much more extended period of time. If we look at the gastrocnemius muscle, which is also called the calf, most people call it the calf muscle, it's kind of a combination of both. There is both white and red fiber, both slow twitch and fast twitch muscle present in the gastrocnemius, so it qualifies as both. It can be both in some cases, in some aspects, in some instances, more of a fast twitch, and in other cases, much more of a slow twitch type muscle. All right, so this is again is an idea of what occurs over a period of time when you're exercising. We look at, within about 6 seconds, you've got enough ATP stored up in your muscles to last for about 6 seconds of fairly strenuous exertion. For about 10 seconds, the creatine phosphate is going to kind of help pick up the slack and help recycle ATP. Between 30 and 40 seconds, all the way pretty much up into the end of your exercise, then you're dealing with glycogen you have stored up in your muscles. So glycogen is converted to glucose. Glucose is then converted to ATP. We can look at both anaerobic and aerobic respiration. This is anaerobic over here with lactic acid versus aerobic over here where we have oxygen available. If you've ever heard the expression hitting the wall, so if somebody were to exercise for such an extended period of time, maybe they're running a marathon, if they exercise for such an extended period of time, they completely exhaust their glycogen supplies. That's where you get to the point where you quote-unquote hit the wall. And it takes a bit of time for your body to adjust and find other stores of energy to keep you going if you do reach that point. If you do go into oxygen debt, as other debts are concerned as well, the oxygen debt must also be paid off. So if you go to the point where you exercise anaerobically, there is a period of time where you actually do need to, your body needs to kind of reacclimate itself after that. So deep breathing, creatine phosphate storage restored, myoglobin is restored with oxygen, glycogen is built back up again after a meal, all those things. I mean, these things don't happen the next second. They take a bit of time. You got to consume another meal to build up glycogen, for example. So it does take a bit of time to pay back that oxygen debt. And then finally, as far as building muscle goes, if you are someone who's inclined to do such activities like weightlifting, one thing that's kind of important to remember is that when you lift weights, if you build muscle, the overall number of muscle fibers you have does not change. Skeletal muscle cells in particular are not very good at dividing. And so when you build muscle, when your muscles physically get bigger or firmer or those kinds of things, you're not actually changing the number of cells you have, you're changing the size of the cells you have. So the cells are going to go into what's called hypertrophy, or sort of building themselves up into larger and larger states. So they're actually going to have more myofibrils. Remember, myofibrils are made up of both thick and thin filaments, the myosin versus the actin filaments, and so on. And the more of those myofibrils, the more of those protein fibers you have, the more volume or the more space your muscles are going to take up. So in other words, they're bigger if you increase the number of myofibrils. So stimulating them to take up protein, build more myofibrils, muscles are going to get bigger. Muscles are also going to get stronger because you have more fibers that are involved with contraction. So that's where we start seeing increases in strength and also increases in muscle mass when we have more myofibrils per muscle cell. But again, the number of muscle cells doesn't change. Aerobic exercise is a state you're in when you're exercising to the point where your cardiovascular system can keep up with the amount of O2 you need to supply your body with oxygen for exercise. This would be more of the type of exercise where you want to increase endurance, so running and elliptical machines and bikes and those sorts of things. Those are more of an endurance type conditioning, whereas you want to try to build more blood vessels, you want to increase vasculature, you want to increase the efficiency of your heart and the efficiency of blood delivery to tissues in your body. All of those things are going to result from aerobic exercise. This actually does change, even on a cellular level, the construction of your cells. After a fairly extensive amount of aerobic exercise, you can actually start to have more mitochondria per cell, which, in addition to having more oxygen available, is going to allow you to make more ATP and allow you to maintain the level of exertion over a longer period of time. So if when you first start out running, you can barely run half a mile, but after a year or two of training, you can all of a sudden maybe get to the point where you're thinking about running a marathon. There have been actually cellular and tissue level changes in your body as a result of conditioning that allow you to get to the point where you have more endurance, more stamina. In this case, aerobic exercise doesn't typically increase size of muscles, but it increases efficiency of the cardiovascular system. Resistance exercise, on the other hand, is where you build strength. And so kind of the general rule of thumb is that muscles will get bigger when they have to exert 75% or greater their maximum force. So if you can lift 200 pounds, right? If you can lift 200 pounds, you need to be at 75% or more of that to actually build muscle. Okay, so it's a fairly heavy amount of weight that you have to do to build strength. And of course, you have to do repetitions of that as well to begin to build muscle. So any sort of weightlifting exercise, your curls and bench presses and deadlifts and squats and all that kind of good stuff, those are going to help build muscle, and those are more anaerobic type activities. All right, so that's the end of our chapter on the muscular system. So we're going to cut this off here, and I will get it posted.